All right, so this will be more examples for section 2.3, and some of these will use the product rule maybe, or the quotient rule, depends on the scenario. Something I did not go over in the previous videos is, if I can find it, yeah, so this is theorem 2.9 in the section, just more trig function derivatives. I did not mention these. These are 4 more derivatives that we can add to our list. And right now, so the previous section, we got the derivative of sine was cosine. And then the derivative of cosine is negative sine. So combining all this, this is all of the derivatives for the 6 trig functions. So I would recommend pausing the video and writing these down. These are also in that table of derivatives that I mentioned in one of the earlier videos. Okay, so we'll use those when applicable. So here are the remaining examples for the section that I have not gone over yet. And some of these I might use a product rule, some of them are a quotient rule, or I might not. I might just use techniques that we've already learned from the previous section. So number 23. All right, so even though there's a fraction, and I guess technically you could do quotient rule, but I think it's easier to just rewrite this, and I can rewrite it as x cubed divided by 3, and then plus 6x divided by 3. Since that's how fractions work, we can separate into 2 fractions with the same denominator. And for the x cubed over 3, I tend to write it as 1/3. X cubed is just a preference thing. I just like looking at it with the 1/3 in front. And it turns, for me, it's easier to keep it like that when I find its derivative. Now 6 divided by 3 is 2, so this would be plus 2x. All right, so I rewrote it, and now I'm going to find the derivative. All right, so for the derivative, it's going to be y prime equals, and then I factor out the 1/3 and take the derivative of x cubed, and I use the power rule. So based on the power rule, you drop down the exponents to be 3x to the 3 minus 1. And then plus 2 times 1, since the derivative of x is 1. So the derivative, y prime, you notice the 1/3 and 3 cancel, so I get x squared plus 2. And that's going to be the answer. I didn't apply any product rule or quotient rule for that one. I just rewrote it and used the rules that we're familiar with from the previous section. It was easier for me to do that than instead of using the quotient rule, because there's a 3 in the denominator, but to me it's just easier to do it this way. So that's 23, 27. Yeah, and you could use quotient rule because there's a fraction, but instead I'm going to rewrite it and just combine the x's together since I have x to the 3/2 divided by x. By rule of exponents, this is 4x to the 3/2 minus 1. Right, because technically there's a 1 for the exponent of x, and then I subtract top exponent minus bottom exponent, so it's 4x to the 1/2. Which we know is 4 square root of x, but I'm going to keep it like this so it's easier to find its derivative. All right, so y prime is equal to, and then I do 4, and then focus on the x to the 1/2 using the power rule. So it'll be 1/2 x to the 1/2 minus 1. And we know 4 times a half, so that's going to be 2. So y prime is equal to 2. And then that's x to the negative 1/2. Which I could rewrite this so that there's no negative exponent by bringing it to the denominator. But we know the 1/2 power is the same thing as square root. So this is equal to 2 divided by square root of x. That is the derivative. All right, so that's that one. Now the next one is number 29. All right, so this thing, so I'll make a comment, and actually in the notes on Blackboard or at the worked out examples, I do it the way that I'm going to write this comment. So comment, you could go ahead and apply the quotient rule. That's how I do it on Blackboard in the worked out examples. So for the video, I'm going to do it a little bit differently. So what I'm going to do is instead try to factor and divide out common factors. If there are any, and make note of any discontinuities when I divide out the common factors. So what this does is I'm rewriting f of x into a different function. So we're rewriting f of x into a different function. G of x, where g of x is equivalent to f of x, except at the one point, and that point is the value that they cancel out. And there's a theorem dealing with continuity, continuous functions, that I can do this, and derivatives is a continuous function. So we're allowed to do this rewriting. All right, so let's see, continuous theorem. And the theorem is, let me pull out the textbook. Theorem 1.7 on page 66 is why I can do this. Okay. So for our purposes, I'm just justifying why I'm going to do this process of rewriting the function by canceling out common factors if that's possible. And once I cancel out the common factors, then the result is a new function. And that new function is g of x that I'm calling g of x. And it's going to be equivalent to the original function except at one point. And that one point that it's not equivalent to is when you cancel out the common factors. And that gives you either probably a hole in the graph. All right, so this is the logic. Now I'm going to actually work out the problem. All right, so I'm going to factor numerator and denominator. For the numerator, I'm going to just go ahead and rewrite it so that you have negative x squared first, then minus 3x plus, and then plus 4. You don't have to do that. Just for me, it's easier to rewrite it in this format. So for the factoring. On the denominator, I have x squared minus 1. That's a difference of squares, so that factors in the x minus 1 times x plus 1. I don't know why I didn't mean to put plus 4, so x minus 1 times x plus 1. Now the numerator, because there's a minus sign next to the x squared, I'm going to factor out negative. And that changes these signs. So we get positive x squared plus 3x and then minus 4. Just because I like to go ahead and factor out the negative whenever the leading term has a negative. All right, and then the numerator I can factor. So it's going to factor into two factors where they add up. They multiply to give you negative 4 and add up to give you positive 3. And that's 4 times negative 1. So it's going to be x plus 4. And then x minus 1 are the two factors. Now notice I have x minus 1 top and bottom. Those cancel out. That means I'm going to have a discontinuity. And it's going to be a hole at x equals 1. So the result I get is negative, and then parentheses x plus 4 over x plus 1. And you can think of that as the new function. So like g of x negative in x plus 4. X plus 1 is the resulting function after I cancel out those common factors, and this is the function g of x that's equivalent to f of x, except at the point x equals 1. All right, so keep in mind there's a discontinuity at x equals 1. So now I'm going to go ahead and find the derivative. And I have a fraction, so I'm going to use the product or quotient rule. So I'm going to pause it and write the quotient rule real quick. All right, so this is the quotient rule. I did just a comment that there is that discontinuity at x equals 1 because there's a whole, this is a removable discontinuity. And now my function, because there's an x plus 1 in the denominator, just there's another discontinuity, and it's x equals -1, and that's non-removable. That should be a vertical asymptote. So non-removable discontinuity at x equals -1 due to the x plus 1 on the denominator. All right, so for our function, so this is the quotient rule. I'm going to go ahead and write g of x with the negative sign distributed inside. So it's going to be -x minus 4, and then divided by x plus 1. And so my top function is -x minus 4, and then the bottom function is x plus 1. So the top function derivative taking the derivative of -x minus 4. Well, we know the derivative of x is 1, and because there's a negative sign in front of the x, that's going to make this negative and then 1. And then technically that's plus 0 due to the derivative of 4, since it's a -4 is a constant, and that derivative is 0. So the result is just -1. So I'm going to erase this and just go ahead and write it as -1. Now the bottom function is x plus 1. If I take its derivative, we know the derivative of x is 1, and then derivative of 1 is 0, since that's a constant. So b prime is really just 1. I can go ahead and erase that. And now I can find the derivative. So the derivative g prime of x is going to equal the bottom times derivative of the top function. So the bottom function is x plus 1. Derivative of the top function is -1. Minus the top function over times the derivative of the bottom function. So the top function is -x minus 4. Derivative of the bottom function is 1. All of that divided by the bottom function squared. So that's x plus 1 squared. All right, so now it's just a matter of simplifying. So this will distribute the -1, so that makes that -x then -1. And if I were to, and then this is 1 times -x minus 4, so that's just -x minus 4. And then I have this negative that I can distribute that. That makes this plus x and then plus 4. All of that over x plus 1 squared. So I can cancel out negative x with x and then add negative 1 plus 4 to get 3. And then it's 3 over x plus 1 squared, and that's going to be the derivative. Keep in mind that I can't have x be 1 from that hole in the graph, but I canceled out. And then I also can't have x be negative 1 due to the discontinuity of the vertical asymptote. So x can't be 1 or negative 1. All right, so I think I'll stop it there and do the remaining examples in another in a separate video.